happy, happy to have you back. And yeah, please go ahead with your second lecture.
All right, so thanks again. Thank you all for coming back. Don't be shy. Tell me what you're thinking. So let me just remind you a little bit where we were. So this was the first thing I drew, was this kind of plan, and in the first talk we talked about entirely about this first case of n equals 2 theory is called Lagrangian field theory. And I think for today, we'll continue just to talk about Lagrangian field theory. By the end of the talk, I hope to have got to this corresponding complex integrable system. So the general structure is that for any n equals 2 field theory whatsoever, there's going to be a corresponding complex integrable system. In particular, for Lagrangian field theory, there's going to be a complex integrable system. And in particular, in the last talk, I was talking about a very specific Lagrangian field theory, namely n equals 2 super Yang-Mills with a gauge group SU2. And I claimed that it's related to the Donaldson invariance. So I'll remind you, for a Riemannian manifold, for a Riemannian compact 4 manifold, x comma g, there's some corresponding invariance which Donaldson defined in terms of integrals over instanton moduli spaces. And so my first aim here has been to explain how these invariants are, according to Witten, come from a 4-dimensional quantum field theory, namely n equals 2 super Yang-Mills, with gauge group SU2. And so last time I got as far as saying that, first of all, that field theory is a Lagrangian field theory. That means that it comes from the quantization of a classical field theory, which means in practice that given a 4 manifold, we're going to write down some space of fields. And here was the boson part of that space of fields. So the fields were a G bundle with connection and a section of the complexified adjoint bundle and these auxiliary fields. And then I wrote down an action, or at least the boson part of the action, which is to say, so this is literally a function on the field space. Here is that function. It's an integral over the manifold of some combination of the self-dual and anti-self-dual curvatures of the connection, plus the derivative of the scalar field. And when I wrote it last time, I forgot to write down, you'll see here, this imaginary part of tau. Last time I forgot to write that imaginary part of tau. At this moment, that probably seems just 100% irrelevant to everything, but in a little while, you'll see why I'm fussing about that. And then the very last thing I told you was that this field space carries an action of a certain super Lie algebra. And moreover, the function is invariant under the action of that super Lie algebra. And the super Lie algebra I called, is what I called A, n equals 2, d equals 4. So this is a kind of universal algebra. It's the same for every n equals 2 theory. So this is just some universal object that acts on supersymmetric field theories of this kind. And so not only Lagrangian ones, but all the n equals 2 theories are acted on by this same algebra. But in particular, in Lagrangian ones, you can say very concretely what it means to be acted on by this algebra. It means just that this algebra acts on the field space, and that the action function is invariant. So as I said, it has an even part, which is just the isometries of the space-time. And to be concrete in defining the algebra, you take the space-time to be R4. So literally the isometries of R4 lifted to the spin group. That's the even part, well, extended by these two central generators, which will play a fairly minor role for a while. Plus, the part that's kind of novel in supersymmetric theories is the odd part, which is these 4 copies of spinor representation. Well, 2 positive spinors and 2 negative spinors. So those are the extra generators, which I call Q, following the standard notation. And here concretely is the actual algebra. So the bracket the anti-commutator of odd generators giving you even generators. Okay. Now, so that algebra kind of operates behind the scenes to organize everything that happens in a supersymmetric, in n equals 2 supersymmetric field theory. Now, let me describe it in a slightly sharper way. So here I was writing down the algebra as a representation of the spin group. So in fact, this algebra is a representation not only of the spin group, but also of the other symmetry, the internal SU2 symmetry of the theory. So it's a representation of I spin 4 cross H. I'll remind you that H was just the SU2 global symmetry or R symmetry. So this is a symmetry that I said acts on the field space, but it also acts on the algebra and acts compatibly on the algebra. When we write it as a representation of the spin group, in addition to this SU2, then we see, so before, it might have looked a little funny, we just have 2 copies of everything, but now, when we write it as a representation of the R symmetry as well, then the statement is that we have, it's not just 2 copies of S plus, but rather it's S plus tensor with the 2-dimensional representation of SU2. So I'll write it this way, C2 sub H, meaning that that's C2, or maybe better, let's write it like this. C2, which is a representation, the non-trivial 2-dimensional representation of H. Direct sum S minus tensor C2. Also acted on by H. So that's the slightly more professional way of describing this algebra, and the way it transforms under R symmetry will be important in just a second. All right, save file. Great. So now, for the application we have in mind, it's convenient to do something that actually makes the symmetry of the thing somehow a little less manifest, the symmetry of the thing in R4, but it allows us to formulate it not only on R4, but on any 4 manifold, so it's a good idea to do it. And that's the following. I'm going to consider a different action of I spin 4 on the supersymmetry algebra. Well, it'll come from the action of I spin 4 cross H. So I told you already that I spin 4 cross H acts as symmetries of the supersymmetry algebra. It was naturally a representation of this product of groups. And so when you think of how I spin 4 acts, you would usually think, okay, inside of I spin 4 cross H, I just use the usual action of I spin 4. There's another thing you could do, which is embed it into I spin 4 cross H with the identity map on the first factor, and then some non-trivial hum from I spin 4 to H in the second factor. So rho is going to be a map from I spin 4 to H. So this is a general thing that you can do. So this goes under the general name of twisting, and it occurs in many dimensions. There's many different examples of this kind of basic phenomenon where you have a supersymmetric field theory. It has the supersymmetry algebra is acted on by some Poincare symmetry. In other words, the isometries of R to the n, and also by some other group of automorphisms, which is called the R symmetry. And then you take a hum from the Poincare symmetry to the R symmetry. In this particular case, the one we're going to take is, well, so let's project off the translations. So we just map it to spin 4. what's spin 4, but SU2 times SU2. H, on the other hand, was SU2. And so what we'll do is we'll just take the map that's, say, projection on the first vector. So we'll map G plus G minus just to G plus, or G minus, doesn't make a big deal which one. So that gives us now some kind of twisted action of rotations on our supersymmetries, where now a rotation now acts by a combination of what the rotation used to act by and an additional R symmetry generator. The important feature of this is the following thing. So now let's decompose. Let's now write as a representation of I spin 4. And now this new action, by the way, doesn't commute with H anymore. So it doesn't make sense anymore to ask how it is as representation of I spin 4 cross H if I use this action of I spin 4. It's in that sense that this description kind of reduces the manifest symmetry. But still, let's work with this description. Then this supersymmetry algebra decomposes like this. So again, we have the even part where we haven't changed anything. Why? Because H acts trivially on the even part. So mixing with the action of H doesn't change anything about the even part. This is the even part. But now the odd part, so before I wrote it as some bunch of spin representations. Now it's not that anymore. Rather, it's one copy of the vector representation, 4-dimensional, plus one copy of the trivial representation, 1-dimensional. And then there's the self-dual forms. Let's write it like this, wedge 2 plus of the 3-dimensional. So it's 4, 1, and 3. So it still adds up to 8 like before. We've just kind of reshuffled how they're labeled. So now I'm going to give them names. I'll call these ones, these ones that transform in the vector representation, I'll call them Q mu. So they're kind of naturally labeled by the directions of spacetime. This one, which is just a scalar, so that's something which now, with respect to these new rotations, appears to be just rotation invariant. And I'll just call that one Q. And then these, I guess I would call Q alpha beta, but I'm not going to use them for anything. And so, okay, so all I'm saying is that before we had these maybe slightly complicated looking things. We had, Q alpha and Q alpha dot, which are all labeled by spinor indices. After making this twist, in some way, it looks kind of simpler. For those of us who aren't super spinor minded, now we have a Q which has no transformation law at all under rotations, and this Q mu, which just transforms as a vector. It transforms in the way that translations transform. And now I can rewrite the brackets. Well, I'll just write the ones that are important for us. So Q, its anti-commutator with itself, with Q, is actually 0. It doesn't have to be, right? It's symmetric, so it could have been non-zero, but in fact it's 0. And the bracket of Q with Q mu, so it has to be some even generator. And in a sense, the only real candidate around is the translation in the mu direction. And sure enough, that's what you get. So that's a manifestation of, so before we had this complicated thing involving the gamma matrix, but you see P mu did appear on the right side. After we've relabeled things, that P mu just appears as the bracket of this universal Q with Q mu. And those are the only ones that I'm going to need. So I won't write the ones involving the self-dual tensor. Okay, so I want to say again, this is literally the same algebra as before. I'm just describing it in different notation. But this notation is the one that's closest. First of all, this is the notation that's closest to the theory of, like Tudor has been talking about topological field theory. If you were deriving a topological field theory, if what you wanted to do is derive a topological field theory from n equals 2 super Yang-Mills, you would use this twisted language, and this Q would be his BRST operator. Okay. Okay, now, so far that's just some relabeling of this algebra that I told you about. But now, yeah, I guess I want to do it in this order. Yeah, so let's talk about the twisted theory. And what I'll mean by the twisted theory is just so given X, a Riemannian four-manifold, given a Riemannian four-manifold X with a spin structure. Now we can do the following thing. So I told you before that this n equals 2 supersymmetric Yang-Mills, you could formulate it on Riemannian manifolds with spin structure with an SU2 connection. And now let's do that, but in a very specific way. So, so we're going to introduce. So now we are going to put an SU2 connection on it. And how do we get it? So remember, H is just another name for SU2, but not the SU2 that's the gauge group, a different SU2. Over X, we're going to introduce an H bundle over X. It's not going to be integrated over. It's not one of the fields of the theory. It's just a fixed SU2 bundle. The way we get it is we'll take the projection of the Levi-Civita connection along. So the Levi-Civita connection is a connection for the group, well, a priori SO4, right? But because this manifold has a spin structure, the Levi-Civita lifts to spin 4, which is nice because that means, so it's SU2 cross SU2. And so we could just project it along, say, the first factor to SU2, which is H. So I'll make an SU2 bundle that way. Okay, so we said that the theory can be coupled to any background SU2 fields. In particular, I could couple it to this very special background SU2 gauge field, to this very special H bundle. And then the kind of cool payoff of this. So then, and we can define the field space of X with this background H bundle. I didn't give this background H bundle a name. I should give it a name. I guess I'll call it P. So X with this background H bundle. And it would look essentially as before. Before I wrote it for R4, but essentially you make the obvious modifications of that to account for this, to account for the fact that you put it on a general Riemannian manifold. And now the payoff, the cool thing that happens here that wouldn't happen if we didn't do this funny coupling to an H bundle is, so we define f of xp, and we also define a function s. So if I call this just f, we also have the action function as before. Is that this field space now has an odd symmetry. So it has Q. So we don't have the whole supersymmetry algebra acting when we put the theory on an arbitrary 4-manifold. And you can kind of see that you couldn't, right? Because the supersymmetry algebra contains in particular the isometries of R4. Well, the general 4-manifold doesn't have the isometries of R4. In fact, the general 4-manifold doesn't have any translations. So it looks hard to have this supersymmetry algebra acting. But if we set things up in this very particular way, we introduce this coupling to an H bundle, which is, in a certain sense, it's equivalent to considering the action not of rotations, but of these twisted rotations. And so then what we'll get is we'll have one odd symmetry still acting. So if you like, it's kind of a generator of the Lie algebra of like, you know, R0/1. Lie algebra R0/1. It's just a abelian Lie algebra with one odd generator. Q acting on F, preserving S. It was like a real shadow of what we had before. Before we had, in R4, we had, you know, 8 supersymmetries. Now we just have one with Q squared equals 0. But that one is still pretty good. Okay. Okay, so now we're studying we're trying to define the path integral of n equals 2 supersymmetric Yang-Mills theory placed on a general Riemannian four manifold in this very particular way. So now, okay. So now we want to do it, right? So we want to compute. Let's start with the simplest thing, the empty correlation function, or the partition function, which is supposed to be, equal sign in quotes, is supposed to be the integral over this field space of some measure of e to the minus the action. And so in a general QFT setting, this would be hard. Essentially, the only general techniques that we have available are, on the one hand, perturbation theory, which involves expanding around like a Gaussian integral, or like numerical lattice simulations, where I would take my space-time, lattice-ize it with a huge number of points, try to do some discrete version of the path integral. Then you have to deal with hard questions of, you know, what happens when you make the lattice finer and finer. So in general, okay, I mean, so there's a huge body of literature on how you might try to do it, but at least it's generally something hard, and you don't typically expect to get an exact answer. Here, the situation is very different. And it's different exactly because we're in this funny situation of having a field space which has one odd symmetry acting on it. So this Q symmetry helps us here. Why? Well, the basic philosophy is like this. This is the kind of formal path integral argument. Well, let me right away say what's the name of what we're going to do. So this is the thing I'm about to explain is something called supersymmetric localization, and it's this tool that people are constantly using in whenever they want to compute something in a supersymmetric quantum field theory that comes from a Lagrangian. This localization is kind of the go-to tool. So the basic philosophy of it is like this. The crucial equation is, you know, for any local operator, or even string of local operators. We'll start with one local operator. That the vacuum expectation value, so the expectation value of the operator O could be anything. But the expectation, suppose you take your operator and you act with Q on it. So the space of fields, we said, is acted on by this operator Q, and that action also acts on the space of local functionals on the fields, essentially by just duality. And the claim is that this is 0. This is always 0. That's provided I didn't insert anything else. This is supposed to be 0. Why? Okay, so you could just take this as kind of an axiomatic fact. That's part of what we mean by having a Q symmetry. But, you know, why should it be true? the sort of path integral reasoning for it. Well, what is the expectation value of QO, right? So what does that mean? By definition, it means that I have to do the path integral with this QO inserted. So I integrate over the space of fields QO. Now, this Q is like an action of, okay, it's a super vector field, but the fact that it's super is not particularly important for actually most of this story. And in particular, it acts on functions obeying the usual Leibniz rule, the same as the action of an ordinary vector field would. And remember that the action S is invariant. So Q of S is 0, right? If you have a function that's invariant under some vector field and you act with the vector field on it, you get 0. So likewise, Q of e to the minus S is 0. So because of Leibniz rule, then this is the same as Q acting on the whole O e to the minus S. That's the idea. And now so now you've got the integral of Q of something. And so now here comes the second, slightly optimistic step. And again, this is not something really special to having an odd symmetry. What this says is that the integrand is a total derivative. So you're integrating something which is the derivative of something. And so that integral should reduce to just a boundary term. And that boundary term, so okay, if you're a little optimistic about how things behave near the boundary of field space, you would say this is just 0. Okay, so that's the kind of sketchy path integral argument. I guess a slightly more complete argument would include the statement that Q preserves the measure of integration. Let's let that go for a second. So that's the idea. That's the idea of this argument. Now, how does that help you? Okay, so far it's not clear why that would help us to compute the path integral itself. But now so that's kind of step 1, is to know that equation. And now step 2 is you do the following thing. You say, pick some operator psi. Again, this is just going to be a function on the field space, but I call it, confusingly, we tend to call functions on the field space local operators. Anyway, it's some function on the field space. So I from F to S. Yeah, it'll be the integral of a local operator. Maybe it's just best to write psi from F to S, prejudicing ourselves about exactly what it is. And then we can imagine doing the following thing. We could deform our quantum field theory, by which in practice I just mean deform the action. I'll change the action S to S plus some parameter T times Q psi. And let's think about what's the effect of this deformation. Well, on the one hand, so let's ask concretely, so to understand how this deformation acts, we could ask what's the T derivative of the partition function? Well, okay, so again, let's just write the formal path integral thing. So that's the derivative of the integral of e to the minus S plus T Q psi, right? And what is that? That's, well, the T derivative just pulls down a copy of the Q psi, right? Q psi e to the minus, I guess with a minus sign, it's not going to matter. S plus T Q psi. And now, so what's that? Well, that's the expectation value of the operator Q psi. But now, crucially, this new action S still conserves the Q symmetry because Q squared equals 0. So for every value of T, not only at Q equals 0, this expectation value of Q psi is going to be 0 by the argument that I told you above. And so the conclusion is that the partition function of this theory, which we wish to calculate, whatever it is, it's going to be independent of T.
Excuse me, in your averaging now you have a different action, right?
Absolutely, I have a different action, but this different action still has the property that it's
Right. No, I was just curious about notation. So in fact, you should have like T whatever.
Yeah. So I just put a little T under the.
Correct. No, I understand. Okay, fine.
No, but you're absolutely right. You're absolutely right. But fortunately, the theory is Q invariant for every value of T,
yeah.
so it's okay.
Yeah.
So this Z, whatever it is, it should be independent of T. But now you have the following idea. You say, well, maybe I can use that freedom to simplify the computation. So we can attempt, and in practice, it turns out to be possible to do it. Now the idea would be to choose psi so that you might first think that by choosing psi appropriately, you could just prove in this way that Z equals 0, right? Because we're going to add e to the minus T something. So if I could choose psi so that Q psi is just some enormous positive number, then what I would prove in this way is that Z equals 0. Well, if you think about it, you can't quite do that. Again, the intuition that Q is like a kind of vector field is not too bad here. If you have a vector field, Q acting on some function will be 0 at the zeros of the vector field, right? So the best that we could hope to do is to arrange that Q psi is positive, not everywhere, but everywhere away from the zeros, everywhere away from the Q fixed locus in F. So I don't know kind of a universal way of doing this, but in specific examples that you try to do, for example, in this n equals 2 Supergang-Mills theory, you can find a psi with this property. And therefore, by just jacking up this parameter T, I hope it at least seems reasonable that the integral is going to get localized to an integral just over the Q fixed locus. Because you can suppress by an arbitrary amount the contributions from everywhere else. So you'll be able to reduce it to an integral over, and what you really do is you reduce it to an integral over a very small neighborhood, but then you do the integral in the normal direction, and then you're left with an integral just over the Q fixed locus.
So this is a little bit like a stationary phase method, right?
It's very much like a stationary phase method. And there's examples, God, I don't remember this stuff as well as I should, but there are these theorems like Twister-Meyer-Heckman theorem that says that sometimes the stationary phase
is exact. Can be exact. Yeah.
And those examples can actually be proved in this way, or well, maybe proved. They can be thought of in this way. You kind of embed your integral into some supersymmetric setup. Yeah. Indeed. So we reduce Z in this way, at least formally, to an integral over the Q fixed locus. Okay, so that's great. So we started with an infinite dimensional integral, and now we're very lucky. And in this particular situation, we can reduce it to to an integral over something smaller. And in this case, it turns out to be something finite dimensional. So what I wrote here is pretty generic. You could imagine doing it in all kinds of situations. In the case of where we've been studying, where T equals n equals 2 Supergang-Mills with gauge group SU2, this Q fixed locus, so the Q fixed locus inside of F, is equal to the instanton moduli space. So you just look at the equations that define the Q action. And you discover that the fixed points are exactly the instantons, the solution of the anti-self-dual Yang-Mills equation, which I wrote at the beginning. And so in this way, again, you can see it's kind of formal argument, but formally what you recover is, so our partition function is equal to the partition function, I'll write it like this, angle brackets sub Donaldson. That's the thing that I told you about at the beginning. Donaldson's invariant, which just counts. So here so far we're only going to get a non-trivial contribution from the zero-dimensional components of the instanton moduli space. Yeah, that's actually, okay. I guess I didn't quite say that. That's an important point, is that here, when you actually go to do the integral, what you'll discover is that the integrand, in fact, is zero unless you're on a component of the dimension of the instanton moduli space of dimension zero. And then what you'll get is exactly the Donaldson invariant in that situation, which is a kind of signed count. You count the instantons with a plus or minus one. Yeah, I guess I should have explained why the dimension, why you only get a contribution from zero dimensions. That's essentially because supersymmetry pairs up the zero modes in the bosonic directions with the zero modes in the fermionic directions. Okay, never mind. Anyway, that's the statement. So okay, so now I've told you how quantum field theory formally recovers at least one of Donaldson's invariants. And then you guess, what about the rest? So what about the Donaldson invariants which involve integrating over, positive dimensional moduli spaces of instantons? Where are those in this story? Well, those don't have to do with just the partition function. They have to do with something a little fancier. So let's talk about that.
So the Q you're saying basically gives a vector field over the space of different action functions, right? Something like that?
Not on the space of different action functions, on the field space.
Field space.
Well, okay, there's two things you could think about. So I guess here you could say, here I did deform the action. That deformation involved Q, but also involved this object psi, right?
Okay.
But like here, when I was talking about using Q as a kind of vector field, odd vector field, but more or less a vector field, what I was thinking of was that we have one single field space and one single action. So we have one space with a function that has a supergroup acting on it, conserving that function. And then we're just exploiting that situation.
Okay. So does it give you a nice U1 action? So it's actually analogous to the Dorsey-Heckman sort of thing?
I mean, it's not a U1 action because it's odd, right?
Okay.
Were it to be an even group, then it would literally be a U1 action.
It's like that's not all vector fields give you those, right? Because it could like not close up nicely.
For an even vector field, you would worry about that. That's right. You would then you have to distinguish those two things. Yeah. I know. Maybe in the next talk I can briefly explain how the Duistermaat-Heckman thing fits into this framework.
Okay, thank you.
I would do it now, but I can't remember it in real time. Okay. Anyway, so where was I? Yes. So I wanted to say, what about the other Donaldson invariants? Which we sort of suggestively wrote in this notation. We wrote them like this. We said there's some cohomology classes on the moduli space of instantons, and Donaldson, also considered the cup products of those, integrating the cup products of those. Well, so this notation, as this notation suggests, those are going to be expectation values now of some operators. So which operators are they? So let's let V be the local operators in the theory. And first, again, I'll talk about them on R4. So And by this, I mean the same thing that Tudor means when he talks about local operators. Except that initially mine is a representation of a bigger space because I didn't do the twist yet. So it's a representation of this whole n equals 2 supersymmetry algebra. And if you try to compute correlation functions of kind of arbitrary operators in there, that'll be basically hopeless. That's as bad as computing in, well, okay, it's not as bad. It's almost as bad as computing in a theory that's not supersymmetric. Anyway, you don't typically expect to be able to get an exact answer, I think. But let's do the following thing. So remember that we have this supersymmetry that I called Q, this odd vector field on the space of fields, which we called Q. Because Q squared equals 0, and Q acts on this space V, so we can consider the cohomology, which I'll call script dr. So the cohomology of this nilpotent operator. So I can consider the kernel of Q mod the image of Q. And so, and if, just as a piece of notation, if Q acting on some operator equals 0, we'll call the operator Q closed. I guess that's the usual terminology when you have a complex like this. The closed things are the ones that are annihilated by Q. Yeah, and if O is Q of something, then we'll call it Q exact. Okay, so we look at the closed ones modulo the exact ones. And now the statement is that the correlation functions, you know, these expectation values, O1 of x1 up to On of xn, so they have nice properties when all the OI are Q closed. So for example, so here are some of the properties they're supposed to have. So, so first of all, it depends only on the cohomology classes, only on the Q cohomology classes of the O's. Second of all, it's independent of the insertion points. So that's very different from what usually happens for correlation functions in quantum field theory. Usually the correlation function is some complicated function of the insertion points. And particularly, it very often has a singularity when the insertion points come together. So in general, that forms a very complicated structure. Here it's much simpler because it only depends on the operators that you insert, not where you insert them. And moreover, it only depends on the cohomology classes of the operator. And then the last thing is it also, and maybe this isn't totally unexpected given that it doesn't depend on the, I said it doesn't depend on the insertion points. It also doesn't depend on the metric. On X. So I guess this is when we put the, so sorry, up till now I talked about the theory on R4, but when we put the theory on a Riemannian manifold, we're going to consider similar kind of correlation functions. And then this correlation function is actually going to be independent of the metric. Modulo a technical thing. It's independent of the metric if B2 plus of X is big enough. And these properties, maybe all I'll say about them is that they follow from the equation that I wrote before. So now I'm going to apply Q to this whole string of operators. But just think of that as a product, as a function on the field space, which happens to be a product. Then this Q would obey Leibniz rule, and so we would say, well, this is the sum from 1 to n of terms where the Q acts on the kind of ith factor. So from that equation, you can kind of formally deduce, and it's an interesting exercise to do it, you can formally deduce the first two properties here. And the third property, you have to know something about how the metric dependence is actually implemented in quantum field theory. It's implemented through a field called the energy momentum tensor, and the energy momentum tensor is Q exact. So that one is a little harder. But anyway, if you're a kind of optimistic person about path integrals and not worried about boundary terms and so on, then you can formally prove all of these things. Then there's also another thing. So this is not, so having these operators is not yet quite enough to get us what we need in Donaldson theory. There's one other thing that we need to do, which is the following. So the Q closed O, so the O with QO equals 0, also have this thing called descendants. So it's exactly the thing that Tudor talked about, but I just want to write, since I'm right here and since I need them, maybe I'll just write a couple of formulas. So given one of these operators O that's annihilated by Q, that's kind of behaves well with respect to the supersymmetry, you can build a bunch of other operators. So what will I do? I'll define O1. So I start with O. Now I'm going to define O1. I'll do the following thing. I'll take, so remember we had Q, but we also had a bunch of other supercharges. In particular, we had these vector ones that we called Q mu. Let's take Q mu and act with it on O, and then multiply that by dx mu. So now I'm making kind of a one form, kind of operator valued one form, where its component in the mu direction is this operator Q mu O. And then similarly, I'll define O2 as Q nu O dx mu wedge dx nu, and maybe I should put a half here. Etc. So similarly, I could define O3, a 3 form, and O4, a 4 form. I guess I could keep going, but all the rest would be 0 because I'm in 4 dimensions. So I started with an operator which was just an ordinary operator. It wasn't valued in forms at all. Or if you like, you could say it's a kind of 0 form valued operator. It depends on just the point of space, but nothing else. And now I defined this chain of 1 form, 2 form, 3 form, 4 form. And now the cool relation that these things obey is, okay, so O had QO equals 0. If I take Q, apply it to O K, I don't get 0, but what I get is D of O K minus 1. So that's an exercise to prove. It follows just from the fact that the crucial thing that you need is that is this relation that I wrote in the supersymmetry algebra, that the bracket of Q with Q mu is P mu. But I mean that seriously. This is, I mean, some things I'm saying are kind of hard to check by yourself, but this is one thing that you can actually do, and you learn something by doing it. Okay, so these are not exactly like Q closed operators, and so if I insert them in correlation functions, these higher ones, you first think they won't have such great properties. All this formal stuff I said above, it was crucial to use literally Q closed operators. But then you might have the following idea. Since the failure to be Q closed is a total derivative, what we can do is we can take these form operators and integrate them over cycles. So what we could do is the following thing. So let's take a cycle. So let's take a cycle in R4, or when the time comes, we're going to do the very same thing in the form manifold. We could define, so this is going to be a K, well, in fact, it could be a K chain. It doesn't have to be a K cycle. Let's define O of gamma. So before we had O of X, the operator, which you think of as being inserted at a point. Now I'm going to do a similar thing where instead of putting it at a point, I put it on this chain. So it'd be an integral over the chain gamma of the K-form operator, OK. Okay, this is so important that it should be in a different color or something. This is important. Okay, so now what's the property that this new kind of, so this operator which we put on a chain, this has the property if I was actually like teaching my Zoom class, I would ask, okay, no, let's not. So the property that this has is QO of gamma is O of the boundary of gamma. That you check just from the colored equations. You'll see that this is true. It's Stokes' theorem. And this was also used, I mean, Tudor used essentially this in at least in one dimension in his talk.
Sorry, I missed that. What?
I was saying that you used this. Didn't you use this?
Oh, I did, totally.
You used it maybe only in one dimension, right? But you used it.
Mm-hmm.
So in particular, if gamma is closed, the simplest thing you could imagine would be that, so it has no boundary. So then this O of gamma is actually a Q closed operator. And so then we can insert this in correlation functions. So now, instead of having the operators inserted at points, I can start with a Q closed operator, take its descendant, and then integrate it over some higher dimensional cycle. And so this has all the same good properties. Well, let's say good properties similar to those of O1 of x1 up to On of xm. I'm saying similar because you know, one of the good properties I said for this product of Q closed operators, one of the good properties I said was it's independent of the xi. Well, what's the analog here of being independent of the xi? It's depending only on the homology class of the insertions gamma 1 up to gamma n. That's another fun thing to check. It only depends on the homology class. And now finally, those are exactly the properties that that Donaldson's invariance had. It was a function of a bunch of homology classes on the manifold, and it depended only on the, it didn't depend on the actual cycles, it depended on just the homology class. That's exactly what we've got here. And so, Witten, in his famous paper, argued that by kind of similar path integral localization to what I told you before, he argued that sure enough, these correlation functions of Super Yang-Mills theory are literally equal to the Donaldson invariance, which now involve integration over positive dimensional moduli spaces. Okay. All right. Well, okay. Now I wanted to tell you about the Seiberg-Witten curves. Okay. Let's just say maybe what the Coulomb branch is, and then next time we'll be in position to talk about the Seiberg-Witten curves. So, so in this story, one of the main players, as you saw, was these special operators in the theory, which are Q closed. So we started with these Q closed operators, which remember just means that they're, if you think of them as functions on field space, it just means they're invariant under some odd symmetry action, some particularly nice functions. Then we would do this descent and we would produce kind of cousins, and then we would compute correlation functions of those cousins. So these are clearly some particularly important operators in the theory. Now, so all right, here's something you could do with them. You could ask, what's the most basic function? What's the most basic question you can ask about an operator? Well, you can consider the correlation function, which is just the 1-point function. now, and now I'm going to ask that question not on a compact manifold, but I'm going to go back to R4. Let's go back to the theory on R4. And let's consider what are all the possible values of the 1-point function, vacuum expectation value of O. And because it's independent of the insertion point, I won't even write the insertion point. The expectation value is just, I just write it like this. For O in this cohomology R. So remember R was the kernel of Q on the image of Q. I didn't tell you one very important thing about R. I didn't tell you why I call it R. It's R because it has a natural ring structure. Why does it have a ring structure? Well, roughly speaking, it has a ring structure because if I consider O of x1, O of x2, so okay, sorry. So if I have O1 and O2 that are both in R, I could consider O1 of x1, O2 of x2. Now that's not a local operator. That's a, that's kind of a composite thing, right? It's one thing at x1 and one thing at x2. But now I can imagine doing the following thing. I'll take x1 and move it very, very close to x2. So let's look at the limit as x1 approaches x2 of the product O1 of x1, O2 of x2. Kind of bringing this one very, very close to here. Well, usually in quantum field theory, that limit wouldn't be expected to exist. You would expect that there's some singularity. And even here, honestly, there might be some singularity. In conformal field theories, I think you can argue that there isn't one, but I'm not 100% sure if there can or can't be a singularity here. One thing you could say for sure is that if I just look at the Q cohomology class of this object, then it doesn't have a singularity because in fact, I tried to convince you before that the Q cohomology class is actually independent of the position. So as I move the operator x1 closer and closer to x2, on the one hand, the Q cohomology class isn't changing. On the other hand, the thing that I get looks more and more like a local operator. I can bring them as close together as I want, and so that's a kind of rough argument that you can construct actually a new local operator by taking the limit as one of them approaches the other. Yeah, in conformal field theory, we could do a little better in the language of the operator product expansion. Anyway, this is at least some rough argument that these operators that R actually forms a ring. So let's call that by definition O1 dot O2 evaluated. So that's going to be our new local operator or our new class in R. So it's a local operator maybe up to Q exact things at x2. And then the other thing you can say for the purpose of studying the 1-point functions, on the one hand, it's a ring. On the other hand, the product, let's ask about the expectation value of the product. So the expectation value of the product, well, as we said, this is really shorthand for inserting these two operators at two nearby points. But then, as I said, that's supposed to be independent of the position. So I could also take the opposite limit, where x1 minus x2, where the distance becomes extremely large. It's supposed to be equal. So, so then I'll just get, well, okay. Now there's an important non-trivial thing, which is I guess you could say it's one of the axioms in quantum field theory, is that when you have two operators and you take them very, very far apart, then the expectation value is supposed to factorize. It's supposed to become just the product of the individual expectation values. So that's to say it's the product O1, O2. So what this says is we've got this ring of functions. If you look at their expectation values, the expectation value is multiplicative. It's compatible with the ring relation in this way. So, so what's the space of all possible one-point functions compatible with this ring structure? Well, that has a name. So the possible values of one-point function. Whoop. Yikes. Okay, my app suddenly closed itself. Yeah, that's disappointing. I'm trying to sell it. I'm trying to say that this app is great. Okay, restore the file, please. Okay, it came back. Yep, it all came back. But I guess I have to reshare it, right? You're not seeing my screen now?
No screen at the moment.
Okay, sorry, I'll just share it and then I'll say literally the last 30 seconds and I'll be done. Have you got it now?
Yeah.
Okay. So the possible values of the one-point functions, possible values of the one-point functions is, I guess in algebraic geometry we call it the spec of R. In other words, the ring R is the, it's a commutative ring, so it's the functions on some space, and that space is the space of kind of possible values for the one-point functions, and so this is what we'll call the Coulomb branch. Well, I guess I'll put it. This is the Coulomb branch of the four-dimensional theory. It's to be distinguished, since in the math world now there's a lot of excitement about another thing called the Coulomb branch of a three-dimensional theory. That's related to this, but it's not the same. Okay, so maybe I'll talk a little more about the reason for this name next time, and then I'll talk finally about the integral system that lies over the Coulomb branch. But I think this is a good place to stop now.
Yeah, Andy, thank you very much. Do we have any questions?
I have a couple of questions, if that's okay, inspired by some things you just said, Andy. So one thing is that, when we say, so maybe just putting on the algebraic sort of geometer hat for a second, when we say spec of this ring, are we talking about the prime spectrum or the max spectrum, or does it not matter at all in this particular case?
God, do I even remember? I mean, okay. This ring, I mean, I was afraid of this. I shouldn't have said this.
Sorry.
Let's say it kind of prosaically in the example that we're interested in, just to be sure that everyone agrees. In the case that we're interested in, what I'll say at the beginning of next time is that this ring is literally free on one generator. So in our example, this ring is going to be there's going to be one generator that generates the whole thing with no relations. And then all I want to say is that in this case, the spec is just the plane. This is like C adjoin X, right? It's polynomials in one variable. And so that's just polynomial functions on the plane. Yeah, in general, I mean, right, what I want to say, when you have some commutative algebra, that's the algebra of functions on some space, right? That's what I mean by spec.
No, that's fine.
I think you can only see the affine spectrum with local operators. The moduli space of vacua may not be affine, but
here it is, right? I'm talking about it. I mean,
yeah, here it totally
I understand
is.
that.
Sorry, yeah.
Yeah, we'll talk about that next time.
Okay, no, awesome. No, that's enough for me for now. And then maybe my other question, also inspired by this, and the comment you made about the 3D picture in Coulomb branches, that these aren't the same Coulomb branches. Because for me, a Coulomb branch is spec of a homology ring, a Borel-Moore homology of a particular affine Grassmannian, that I construct from a group and a representation of that group.
Right.
And then I can interpret that affine Grassmannian part as a moduli space of framed bundles, and then so I'm taking spec of homology of that moduli space. So imagine that. I mean, you said what's happening here is different from that picture, but there must be some connection, right, between calling these two things Coulomb branches.
Well, right. So, okay. So the first thing to say is that they are both instances of the same kind of thing, which is that you first construct the ring of Q invariant for some appropriate Q local operators in some quantum field theory, and then you identify its spec as your Coulomb branch. I mean, the dumb thing to say is just that they're different quantum field theories. So here I'm talking about a specific quantum field theory, which is a 4-dimensional n=2 supersymmetric quantum field theory. The story you're talking about, if I'm not confused, is about a 3-dimensional quantum field theory with n=4 supersymmetry. And there you have a little more choice than but I guess that choice doesn't matter for strictly 3D theory. In what I said, there was essentially only one reasonable choice of Q, the Q that I picked. In the story of a 3-dimensional n=4 theory, there's more Qs available, but I guess the story is basically the same for all. Tudor will correct me if I'm screwing up. He knows the 3D story much better than I. Okay, thumbs up so far.
But yeah, and then no, okay, that's great. And because in the 3D story we have this affine Grassmannian sitting around. Can I see that in the 2D story? Like, is it there, but maybe buried in some other way of thinking here?
You mean in the 4D story, the one I'm talking about here?
Oh, sorry, yeah, in the 4D story, I mean.
I don't think so. I mean, there is a kind of interplay between the two. Okay, so there is a thing that kind of interpolates between the two stories. But I will actually talk about that in either the third or the fourth lecture.
Oh, okay. Well, maybe we can leave it for then.
Yeah. Maybe we could revisit that question then.
Okay, perfect. Yeah.
Hey, can I throw in a comment? So what Andy's talking about here in Donaldson theory is a lot simpler than what shows up in 3D. In particular, it's completely perturbative. This analysis of local operators. The local operators that Andy will discuss are functions of the fields. And there's non-perturbative stuff that involves integrating over instanton moduli space and computing expectation values. But in getting the Coulomb branch, there's non-trivial stuff in Donaldson theory, but Coulomb branch of 4D n=2 theories, as defined here, is a completely perturbative thing. And you get this lovely commutative ring, and you don't have to talk about affine Grassmannians. Affine Grassmannians come from trying to describe local operators in a sort of a state operator correspondence by like surrounding them with a sphere and then quantizing the Hilbert space on that sphere, and that gives you Borel-Moore homology of the affine Grassmannian in the 3D case.
That's really owing to the non-perturbative nature there.
Yes, and that's the correct thing that you have to do to find local operators in general when non-perturbative operators appear, the ones that are not functions of the fields. And that's not the case here, and you don't need to do that.
Okay, perfect.
You would get the same answer.
Yeah. Okay, that's fantastic. Sorry, Andy.
Well, I just want to say that the answer is the same, but the answer is the same in a slightly maybe non-trivial way. I mean, it's true that the ring that you get is isomorphic to the ring that you get in the classical theory. But I slightly hesitate to say, I'm not sure how canonical that isomorphism is. Both rings are freely generated by the same number of generators. In that sense, they're the same. But I'm not sure if it's quite fair to say that analysis is
right.
completely perturbative. The answer agrees with the answer you would get in perturbation. But anyway, I agree it's a lot simpler than this Burrell-Moore stuff. I'm just slightly quibbling.
The product structure or expectation values involve a little more than just doing things classically, but the operators themselves are still just functions of the fields. They're not disorder operators, for example.
The ring of operators is isomorphic to the ring of yeah.
Okay, well, this, I look forward to hearing more about this in your subsequent talks. This is great. Thanks, Andy, and thanks, Tudor, as well.
I hope this is useful for the students here.
Well, we'll see. What about faculty? What about faculty? Could I ask you incredibly mundane questions? I mean, one, would you be able to describe to explain the reason why calling it Coulomb?
Yes, I'll say a little more next time. But in short, the reason is that when you look at the okay, so I described this Coulomb branch so far in a kind of formal way. I said it's the possible expectation values that the fields could have.
Right.
But there's another thing, the way that a physicist would usually say it, which is that if you take this field theory and you study it at low energies, well, said better, sorry, let me go back. The good thing to say, I think, is that this theory actually has a moduli space of vacuum. And what that means is that, for example, the correlation functions of the theory, when you formulate it in R4, are actually not just, they depend, in addition to the things I've already said, they actually depend on the choice of a point of this Coulomb branch. And for every point of the Coulomb branch, there's kind of a whole system of correlation functions where the 1-point functions are what I said they are, and then all the higher point functions are computed using those as a kind of input. So then you can ask kind of an effective question, which is how should I think as a real working physicist about the physics of this theory, keeping in mind that the theory depends on a point of the Coulomb branch? The answer to that is, according to Seiberg and Witten, that the theory effectively around a given point of the Coulomb branch, when you explore it at low energies, it actually looks like a much simpler theory. It looks like a U1 gauge theory. And U1 gauge theory is just another name for Maxwell theory, in other words, the theory of electromagnetism. And in particular, if you have two charged particles, those two charged particles obey the Coulomb force law. So you literally have the Coulomb interaction as like the main long distance interaction that you see when you're on.
And what dimension would that be in? I mean, the Maxwell theory can be formulated in any,
no, 4 dimensions, absolutely. All this is about 4-dimensional field theory.
So it remains 4-dimensional Maxwell theory.
100%.
No energy.
Exactly the usual Maxwell theory.
Mm-hmm.
Well, supersymmetric version of it. But other than that, the gauge theory part is absolutely the usual Maxwell theory.
Oh, I see.
And so the Coulomb just refers to that the Coulomb interaction between between heavy charged particles is the usual Coulomb force law.
Okay, now that explains the reason for naming it Coulomb. I have another mundane question. At some point in your heuristic derivation of some of the properties of correlations, you use this the Leibniz rule. You said, well, yes. You have a Leibniz rule. Now, if you have a singular objects in your theory, Leibniz rule is a very suspect condition. In fact, it requires very, very special care when you have so this works here because what? Because you don't have singularities?
I think ultimately that's presumably right, but I think I'm not well, okay, I mean, the formal thing to say is that, when I said Leibniz rule, I'm really just talking about the Leibniz rule for vector fields acting on some infinite dimensional space. But that space is a perfectly ordinary space with an ordinary function on it,
No,
from
but
that
you
point of
have a
view-
question of smoothness. I mean, you have to, when you act on things that are smooth, that's right. But once things become singular, you have a problem.
Yeah, I don't think that there's anything.
So it must be that there's nothing singular really happening here.
I think that's right. I mean, you know, somehow, if the singularities would be a problem here, then they're being taken care of by the sort of miracles of supersymmetry. You know, some of which I explained, right?
Yeah.
The
And
fact
maybe
that-
there's some form of regularization, even if there are singularities, you may regularize things, and there exist regularizations for which a Leibniz rule is still maintained for products.
Yeah, that's probably a more reasonable way of describing the situation.
Oh, thanks.
You asked Andy if this would be useful for students, and I would say yes, based on what I know about some of the PhD projects that people have. But we could also accelerate this by giving them an assignment that's due on Friday.
Give them a homework. Well, I mean, certainly, I mean, there were a few things that I said, you know, should be kind of exercises. I think they are kind of reasonable exercises. Another thing to do would be to just look up, you know, the actual action of n equals 2 super Yang mills and understand it well enough to understand, for example, that the Q fixed locus is what I said it was. I suppose it would be more helpful if I gave you a reference for that, and I can probably dig one up. Well, probably Witten's original paper must explain it. It's a beautiful paper, actually. It's worth looking at. It's called Topological Quantum Field Theory.
I don't want to make it more complicated, and certainly I don't want to be the one doing the exercise, but would it be difficult? Is it, I mean, it must be known. You were using SU2. Is the transition to I don't know, the compact in general very difficult, or?
Well, that was sort of my question.
Oh, at the level of what I
Oh,
wrote,
you already asked that question. Sorry, then
well, actually, no. I went one step further. I was asking about even non-compact groups.
Oh,
but,
I see.
But Andy had mentioned
so
about
for that,
going
I
to.
refuse to discuss. But
Yeah.
so let's first start with compact group. So certainly for a compact group, you know, semi-simple or reductive group, there everything is exactly the same as what I wrote. I mean, I periodically wrote G equals SU2, but where did I actually use it? First of all, when I said it's equal to Donaldson theory, because Donaldson did SU2. Then I said at some point that the ring of, at the very end, I said that the ring of local operators is free on one generator. That won't be true for other groups. It's true for SU2. But I'll explain what's the general thing. Other than that, I mean, of course, the detailed analysis becomes much harder when you try to go further than what I've said here. But for everything that I've said here, I think it's basically independent of what the group is.
Mm-hmm. Okay. All right. No, thank you. Thanks.
Can I make a quick comment about the Leibniz rule? If there's time.
Sure, go for it.
So if we're talking about the action of Q on these collections of local operators, I think the important thing is that they have disjoint support.
Oh, I see. No, with disjoint support, there's no problem.
And that's exactly so the xi's don't coincide, and so each local operator is supported in the infinitesimal neighborhood of a point.
Right.
The points are all different.
The problems already come from overlapping support. So
and you would never, we would never claim that there was a Leibniz rule when there was overlapping support.
Wait, but just to be sure, I mean, it's not that the functions have disjoint support, right? I mean, right, the function O of x1 and the function O of x2.
Yeah, you are bringing them together.
No, it's not that. I'm just saying, literally, those functions considered as functions on the field space, those functions are not disjointly supported, right? I mean, like if you have a function, just think of this, the space of all L2 functions or something. The operation of evaluation at x1 and the evaluation at x2, or sorry, C infinity functions. The evaluation at x1 and evaluation at x2 don't have disjoint support. right? Because there exist functions which are non-zero both at x1 and at x2.
Sure, sure.
And not saying it the right way.
I mean, I agree with you that the
No,
lack of
but you might be talking about singular support. Because the problem is usually with singular support, not with support per se, but singular support.
No, I meant support as in fields are sections of some bundles over 4-dimensional spacetime, and we're looking at functions on the space of fields that are supported over different points of spacetime. So it's probably something slightly different than what you initially interpreted, as I wasn't clear about that, but that is the condition in physics that you need to get a Leibniz rule, and you can prove it topologically, at least in some heuristic quantum field theory sense. The action of Q is obtained by integrating a particular current on a topological codimension 1 surface, and the fact that it factors is the statement that the homology class of a big sphere surrounding a bunch of different points is
separated.
The same, is the same as a bunch of little spheres surrounding each individual one.
Yeah. Okay. No, that helps. Thank you.